This video is on something called delocalized pi bonding, and it is the last video in Chapter 9, Geometries, VSEPR, and bonding. Okay, so far we have discussed what we would refer to as localized bonding, although we have not used that term, where the electrons in a bond are associated only with those two specific atoms that are in that bond, okay? And that would be defined as local, okay, or localized. So if you think about what it means to be local, like if you, what would be a good example? If you ask somebody, are you local to here? That means like, are you from this area, kind of, right? So localized bonding means only discussing the two atoms that are in that bond. However, often this is an inadequate idea for many molecules, okay? And the molecules that it's inadequate for are those with resonance. Okay, so the big topic here, we're gonna revert back to talking about resonance and how that plays into something called delocalized pi bonding. So if you think about the molecule benzene, which we have not talked a lot about, but benzene is C6H6, and it's a cyclical molecule. So it's actually like, it looks like this. It's kind of, I don't want to say it's a circle because it's not a circle, but it is all connected, okay? And benzene's famous, a famous molecule. So if I draw it like this, there's an H on every carbon, and then there's these alternating double bonds. Well, you should also know that, well, couldn't technically my double bonds be in different places? So here's my H's. Okay, so technically, couldn't I have my double bonds here, here, and here, right? And the answer is yes. So this molecule and this molecule are resonance structures for each other. So keeping that in mind, something we want to talk about each carbon is the hybridization of each carbon. So each carbon here has 3 electron domains. So that means every carbon in benzene is sp2 hybridized, okay? And sp2 hybridization would mean carbon, so carbon who normally looks like this, okay, but we know has gone through a promotion. It has promoted that electron. Oops. Okay, and we know that they're sp2 hybridized. And so I'm getting 3 sp2s with 1 electron. And then change my color. And then 2p orbital with 1 electron. So why is this important? Well, it's important because 3 of these bonds are going to be sp2 hybrid orbitals. So like in this case, this guy, and this guy, okay? So those are your sp2 hybrid orbitals on your carbon. But then the discussion is, well, what about this 4th bond, or that double of the double bond? Well, if you remember from a double bond, that anytime we have a double bond, it's 1 sigma and 1 pi. So in this case, if my red is the sigma from the hybrid orbitals, then the double bond, or the pi bond within the double bond, is going to come from this unhybridized p orbital. So what happens, and this is hard to draw, let me try to draw this. Well, I can draw it up here. So every carbon has an unhybridized p orbital, and that unhybridized p orbital is perpendicular to the plane of the ring of carbons. And every p orbital has an electron, right? How do we know that? Well, because we just drew it right here, right? Every p orbital has a electron in it. So as I have it drawn right now, if my double bond is right here, well, then there'd be a pi bond forming right here between those two. And then my other double bonds here, and it would be here. And then my other double bond, and then it would be here, okay? But in my second resonance picture, who also all have unhybridized p orbitals with 1 electron, okay, my double bonds have shifted. So in this case, I'd have my pi bond here, my pi bond here, and my pi bond here. So So in this case, we can no longer use the word localized because sometimes, sometimes the electrons are being shared between these two carbons, but then sometimes it's between these two carbons. So localized bonding, or the term localized, doesn't work here. Because the electrons are kind of spread out among all 6 carbons in the molecule. And so the word here is delocalized pi bonding. So, you ready for the takeaway? How do we know if a molecule has delocalized pi bonds? It's a very simple answer, and the answer is it has resonance. Okay, so that's the takeaway. If a molecule has resonance structures, then the bonding would be said to be delocalized bonding. If the structure does not have resonance, then it would be localized bonding. So there's a practice at the bottom of your paper that says which of the following molecules or ions will exhibit delocalized bonding. Okay, which basically means which of these molecules have resonance. So if you would take a minute, I would pause this video and try this part on your own. Circle the ones or check the ones or whatnot for the ones who have delocalized pi bonding, and then unpause this video and watch my answer. Okay, so here are my answers for who has delocalized pi bonding. So SO3, I'm going to shortcut this because I know you have done it on your paper. SO3 looks like this. It definitely has a resonance, so SO3 has delocalized pi bonding. SO3 minus 2 has 2 more electrons than SO3, and so it actually is all single bonds. It looks like this. And it does not have resonance, and since it does not have resonance, it does not have delocalized bonding. The bonding in SO3 minus 2 would be referred to as localized, so this one does not. H2CO looks like this. Trigonal planar kind of geometry, and this one, although you might be quick to say it has resonance, it does not have resonance because the double bond can only exist between the C and the O. And of course, we can never have a double bonded H, so this also does not have delocalized pi bonding. O3 is ozone, and ozone was actually how I introduced resonance to you. So ozone absolutely has resonance, and so O3, yes, exhibits delocalized pi bonding. And NH4, it's a polyatomic. Ammonium has all single bonds, and so since it has all single bonds, it has no delocalized pi bonding. It only has localized bonding, and in this case it's not even pi bonding because they're all single bonds, so it's all they're all sigma bonds, but that doesn't have anything to do with this question because it does not have delocalized pi bonding. So my only 2 answers were SO3 and O3. So takeaway, if a molecule has resonance, then it has what we describe as the pi bonding being delocalized, which means the electrons are kind of not concentrated on a specific atom. They're kind of